Hey everyone, Victor is here, your organic chemistry tutor, and today I want to tackle probably one of the most confusing topics for many students, the molecular orbitals and specifically the HOMO LUMO interactions. And while molecular orbitals might seem intimidating, I promise you that by the end of this video, you'll be able to identify and properly label the molecular orbitals participating in any chemical reaction with ease. But the first thing first, we need to talk about the terminology and agree what all the terms mean. So first of all, what exactly is the molecular orbital? When we're using a term molecular orbital, we're referring to orbitals that are made by molecules and are within the molecules, but where do those orbitals come from? From general chemistry, we have a good idea about the atomic orbitals. Whenever we have an atom, the atom contains certain orbitals. So if you look at the periodic table, for instance, you probably are not going to have any troubles writing out the atomic configuration for some random atom you're seeing there. So for instance, let's say we take a carbon, which is the core for our organic chemistry. Carbon has the following atomic configuration. We have one s orbital, which is filled with 2 electrons, then we have 2s orbital, which is filled with 2 electrons as well, and then we have a 2p orbital, where we have 2 more electrons. Now, the 1s electrons, these guys, is what we normally refer to as the core electrons, and generally speaking, we're going to make one huge assumption that we are borrowing from the valence bond theory, that the core electrons do not participate in bonding. The next shell, where we have our 2s and 2p electrons, is what we refer to as our valence electrons, and that's what we're going to be using for making bonds. We also know from general chemistry that the s orbital is just a single orbital. However, when it comes to our p orbital is a set of 3 where we have px, py, and pz. So overall, when it comes to our valence level on the second level, we have 4 orbitals overall. And when we take an atom with those orbitals, like let's say carbon atom, and we overlap those orbitals with other atoms, we are going to make some sort of a molecule, and that molecule is going to have molecular orbitals. So in other words, molecular orbitals come from the atomic orbital overlaps. And another important thing that we need to keep in mind is that the number of atomic orbitals is going to equal to the number of molecular orbitals that we are going to end up with. So if I look at something like, I don't know, methane, for instance, CH4, so I have CH4, well, carbon going to bring in 4 orbitals, and then each hydrogen is going to bring 1 orbital, and there are 4 of those altogether. So the total number of orbitals that we are going to have for methane is going to be 8 orbitals, and at the moment I'm talking about atomic orbitals, but we know that since the number of molecular orbitals gets equal to the number of atomic orbitals, that means that when we are going to put all of those atomic orbitals together into molecular orbitals, we are also going to end up with 8 molecular orbitals in methane molecule as well. So if I were to look at the Lewis structure for the methane molecule, which looks like this, then we can see that in methane we have 1, 2, 3, 4 bonds. So bonds are going to be bonding orbitals. Without exception, whenever you see a bond in an organic molecule or in any molecule in general, that is going to be some sort of a bonding molecular orbital. But that accounts for 4 orbitals. What about the other 4? Because we know that we need to have 8 orbitals combined, and so far I'm only seeing 4. Well, the other 4 are going to be what we refer to as anti-bonding orbitals. Normally, we do not show anti-bonding orbitals in any way or form, and normally those orbitals are going to be empty. In other words, they are not going to have any electrons on them. So if I were to draw a very simplified molecular orbital energy diagram, I would show a carbon atom with 4 degenerate sp3 hybridized orbitals, and we would put 1 electron on each, so I have 1 electron here, 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 and there. And I would also show hydrogen, and since we have 4 hydrogens, I would schematically show that I have 4 orbitals coming from the hydrogen as well, those are going to be my s orbitals, and they're all at the same level. And they all are going to have one electron as well. So 1, 2, 3, and 4. Now, when all these orbitals mix up, we are going to make 4 bonding molecular orbitals, which are going to be lower in energy than either carbon or hydrogen atomic orbitals. And likewise, I am going to make a set of anti-bonding orbitals. And here I am again going to make a simplification that all those orbitals are degenerate, okay, in the same energy level. And sometimes you will see that we combine all those energy levels with dotted lines like that, making sort of like a diamond shape. So that should be familiar from the general chemistry. Now, overall, we have 8 electrons, so when I start populating my molecular orbital with electrons, I'm going to go one by one, I will add 4, and then I will add the rest to pair those combined like that. Now, since all of the orbitals that we have between carbon and hydrogen represent sigma bonds, we're going to say that these are sigma bonding orbitals between carbon and hydrogen. And likewise, the anti-bonding orbitals, we are going to represent those as sigma star between carbon and hydrogen. So that is going to be the abbreviation that I'm going to be using for my orbitals. So the first take-home message here is that the number of atomic orbitals is always going to equal to the number of the molecular orbitals when you're putting your molecule together from your atoms. Another thing to keep in mind is that your bonding orbitals, they're always going to be lower in energy than the atomic orbital energy for the atoms that you're using to make those bonds, while the anti-bonding orbitals, those are always going to be higher than the energy level of the atomic orbitals that are making those. When it comes to our electrons, we do want to see electrons on our bonding orbitals, and we do not want to see electrons on the anti-bonding orbitals, because if we do have electrons on the bonding orbital, well, we are creating a physical bond. If we are putting electrons onto the anti-bonding orbital, we are going to be destroying that bond, we are going to be disrupting that. And the final important bit here to keep in mind is that the number of bonding orbitals is always going to equal to the number of anti-bonding orbitals. The anti-bonding orbital is sort of like an evil doppelganger of your bonding orbital. Every bonding orbital that you have in your molecule will always have that evil twin at a higher energy. Now, these were the sigma bonds. How about pi bonds? What are we going to do with those? Well, the idea for the pi bonds is actually quite similar. Let's say we have something like ethylene, a simple alkene with a double bond like that. Well, in this case, we have the sigma bonds that are going to be between our carbon and hydrogen, so I'm going to highlight those in red like this. We're also going to have a sigma bond between carbons, and on top of that, we're going to see a pi bond between our carbons as well. So whenever we have a double bond, we have a sigma bond, and we have a pi bond. And when it comes to the overall energy of the sigma versus pi bonds, typically sigma orbitals, the sigma bonding orbitals, they are going to be the lowest orbitals in our molecule. Then we are going to have the pi bonding orbitals. So the pi electrons, they are always going to be above sigma electrons energy-wise. Then we are going to have our pi star, which is going to be our pi anti-bonding orbital, and finally we are going to end up with the sigma star for our single bonds. So in this case, all of my sigma electrons from my sigma bonds, they are going to be sitting somewhere down there. The pi electrons are going to be sitting above them on that level. That is, of course, a very simplistic representation of our molecular orbital energy levels. However, that is quite sufficient for our purposes, and we don't really need to go into all the gory details about where exactly those levels are, what is higher, what is lower, and all the exact energies. That's unnecessary for our purposes. What we need to know is that the sigma bonds, they are lower in energy than pi bonds, and when it comes to the anti-bonding orbitals, we have the pi star anti-bonding that typically comes before the sigma star, which is going to be the highest anti-bonding energy orbitals in our molecule. And that will become very relevant once we start looking at the orbital interaction between different molecules. But before we jump there is one other last thing that we need to talk about, and that is non-bonding orbitals. In general chemistry, you remember that we sometimes refer to electron pairs as non-bonding orbitals or non-bonding electrons. So if I look at something like methane, for instance, then my sigma bonds and my sigma electrons are going to be sitting on my single bonds, so I will highlight all of them in red. So all of those guys are going to be somewhere down there. In this case, we obviously do not have any pi bonds, so we would not have these orbitals whatsoever. But what about the electron pairs on the oxygen? We have an electron pair here and we have another electron pair on the oxygen. So those would be what we refer to as non-bonding electrons. And typically non-bonding electrons, they're going to be somewhere in the middle. They're going to be neither above the energy of the typical atomic orbitals that combine our molecules, nor are they going to be below. So they're going to be somewhere sandwiched right in the middle. So I'm going to say that my non-bonding orbital is right there. And I am purposefully not specifying that as sigma or pi because, well, it is neither. It is not a bond, so I cannot classify it as either a sigma or a pi bond. These are just non-bonding orbitals. So for our purposes, what you do want to remember is that when it comes to our molecular orbitals, this is the general trend in the energy of the molecular orbitals. At the very bottom, we have our sigma bonds, then we have our pi bonds, then we have our non-bonding electrons, then we have pi star, pi anti-bonding orbital, and then finally we have a sigma star, sigma anti-bonding orbital. And this general picture is going to be true for pretty much any kind of molecule you can think about in the general course of organic chemistry. Of course, sometimes we are going to have non-bonding electrons present, sometimes they are not going to be there. Likewise, pi orbitals, they may be there, maybe not there, it really depends on the molecule itself. And the last bit of information that we need to know before we look at reactions is two more terms. When we are dealing with the molecular orbitals, we are going to be looking specifically at the highest occupied molecular orbital, or HOMO for short. That is literally the orbital with the last electron on it. Typically, the HOMO orbital is going to be either the non-bonding orbital, because that is the highest in energy, usually where the electrons occupy, or it can also be the pi bond as our HOMO orbital, or if we do not have any pi bonds or we do not have any non-bonding electrons, then our highest occupied molecular orbital can be the sigma bond itself. And another term that we need to know is the lowest unoccupied molecular orbital, or LUMO for short. LUMO is literally the very next orbital where you do not have any electrons. So LUMO can be either your pi star orbital, or maybe it can be the sigma star orbital, depending on how the molecule looks like and whichever orbital is right next. Occasionally, depending on the structure of the molecule itself, the non-bonding orbital can also be the lowest unoccupied molecular orbital, which we are going to see in the cases of, let's say, carbocations or boron-containing molecules and a few other examples. Now, here is something important and rather cool about the interactions in chemistry. Every interaction in chemistry is always going to be interaction between a HOMO orbital of one species and the LUMO orbital of the other species. The closer those orbitals are to each other in energy, the better the interaction is going to be. The further away those orbitals are, the poorer the interaction is going to be. That's why some reactions work extremely well, while the other ones, well, they don't seem to be doing anything, no matter how many shamanic dances with drums you perform around them. And once our orbitals interact with each other, the electrons will repopulate newly formed molecular orbitals, which results in us seeing the formation of new bonds and destruction of the old ones. This is a very different mindset from what we are probably used to seeing in the textbook. We normally think about the electrons going somewhere, making bonds or breaking bonds or whatever. But in reality, it's the molecular orbitals or sometimes atomic orbitals that are going to be interacting with each other, and the electrons going to populate the newly formed molecular orbitals. So it's orbitals first, and the electrons flow into whatever space they have allowed for them. So one important thing to keep in mind is that orbitals exist regardless of the electrons being there or not. As soon as we populate the orbital with electrons, the orbital becomes, active, if you want to think about it this way, and it starts exhibiting its influence on the molecule. So for instance, if we're going to populate the bonding orbital, well, we're going to make a bond. If we're going to populate electron density onto the anti-bonding orbital, we're going to break a bond. And if we populate the non-bonding orbital, then we'll have an electron pair sitting on an atom looking all pretty. So whenever we draw any mechanism in chemistry, we are, in fact, showing the HOMO LUMO interactions rather than just where the electrons go. So let's go through a few examples to illustrate that. Let's start with a simple acid-base reaction. I have a water molecule reacting with carb anion. So what we are going to show here in this case with our curved arrows is that carb anion is going to provide electron density to the hydrogen, and that hydrogen is going to release electrons onto the oxygen. That's going to produce the hydroxide anion and methane molecule that I will show like this for right now. Now, from the orbital perspective, what happened here is that these electrons that we have on our carb anion, those are non-bonding electrons. So I will show that as a non-bonding electrons on carbon, or sometimes we just abbreviate it as so, as a non-bonding electrons on carbon. Now, whenever you are giving electrons somewhere, like in this case we're giving those electrons to our hydrogen, the hydrogen needs to accept those electrons. And since we are breaking our sigma bond between oxygen and hydrogen, where the electrons are going to break that bond is the anti-bonding orbital. So we are going to have the interaction between our non-bonding electrons on the carbon and the sigma star that we have between oxygen and the hydrogen. So since the electrons are on the non-bonding orbital on the carbon, that is going to be our HOMO orbital, and since the electrons are going to the sigma star, that is going to be our LUMO orbital. Now, the second arrow here that shows the movement of the electrons between oxygen and hydrogen, well, that one is not an interaction between two different orbitals. The bond that we used to have over here, that is our sigma orbital between oxygen and hydrogen, and it becomes a new non-bonding orbital on the oxygen, so it becomes a non-bonding orbital on the oxygen like that. So it's not an interaction between two different orbitals, so we're not going to be classifying it as such, and we're not going to be assigning any HOMO and LUMO to that. Well, how about something a little bit more complicated? What about a substitution reaction, for instance? Let's say we're going to take the thiolate anion, which is going to be our nucleophile, and we are going to react it with our bromomethane, which is going to be an electrophile in this case. So if I were to draw my mechanism, my curved arrow would start from sulfur and go onto the carbon, and then carbon will release electrons to bromine like so. So in this case, what happens, we are taking an electron pair on the sulfur that is not doing anything, it's not a part of any bond, so that is going to be a non-bonding orbital on the sulfur. Since those are non-bonding electrons, that is going to be our HOMO orbital. We are providing those electrons to carbon, and we can see that we are breaking carbon-bromine bond. So in order to break that carbon-bromine bond, the acceptor of those electrons got to be a sigma star between carbon and bromine, our anti-bonding orbital. So whatever is accepting those electrons, that is going to be our LUMO orbital. Now, as a result of this interaction, we are going to make the dimethyl sulfide. So now what used to be a non-bonding orbital, that is now a newly formed sigma bond between carbon and sulfur. And our co-product in this case is going to be bromide anion, and the electron pair that we now have on this bromine that used to be a bond, well, now that is a non-bonding electron pair, so it's going to be a non-bonding orbital on our bromine atom. Well, let's look at something a little bit more complex. Let's look at, let's say, electrophilic addition to alkenes. If I take cyclohexene and I react it with, for instance, HBr, then we know that our step number 1 here is going to be the electrons of the pi bond going to reach for the hydrogen is going to release electrons to the bromine, and that's going to give us the corresponding carbocation. That will look like that, and of course we have our bromide anion floating around as a coproduct of the first step. If I look at the molecular orbital interactions in the first case, I have electrons originating on the pi bond. So these electrons that I'm going to be giving away to the hydrogen, they are originally sitting on the pi orbital. So that is a pi carbon-carbon bond. And since that's where my electrons are originating, that's where I have electrons, that is going to be my HOMO orbital. Now, I am giving those electrons to the hydrogen, breaking my hydrogen-bromine bond. In order to break that sigma bond, I need to be populating the electron density of the sigma star orbital between my hydrogen and bromine. Since that's what accepting my electrons, that is my LUMO orbital. Now, in the next step of this reaction, the bromide anion going to attack our carbocation, and this is going to give us the final product, bromocyclohexane, that's going to look like this. We can do the same analysis in this case. The electrons originate on bromine. Bromine is not connected to anything, and the electrons that we are using is one of those electron pairs that are sitting on the bromine. So our HOMO orbital is going to be a non-bonding orbital on the bromine, so that is my HOMO orbital. I will write it like that. Now, those electrons are going towards the carbon. I am not breaking any bonds, and what I'm doing here, I am populating the electron density on the essentially empty orbital of the carbocation, which means that the acceptor of the electrons in this case is going to be a non-bonding orbital on the carbon, and that is going to be my LUMO. So you don't always have to give electrons to a sigma or a pi star, sometimes it's just going to be an empty orbital. And the interaction of two non-bonding orbitals in this case going to give you your final product. So the TLDR version here, so to speak, is that for as long as you know your mechanism, you should always be able to determine the orbitals that are interacting based simply on the electron flow. Wherever the electrons start, that is your HOMO orbital. Wherever the electrons go, that is going to be your LUMO orbital. If your electrons start from the electron pair, that's going to be a non-bonding orbitals. If your electrons start from the bond, it's going to be either pi or sigma bonding orbital. If you are breaking any bonds during your mechanism, then whenever those electrons are going to break a single bond, that is going to be populating of the sigma star of that corresponding bond. If you are breaking a pi bond, you are populating a pi star of that bond. And of course, if you are just giving electrons to an empty orbital, you are going towards the non-bonding orbital as well. If you are not sure about the mechanism, however, think about the overall energy for the orbitals and remember that it is always going to be a HOMO LUMO interaction for any type of reaction or interaction in chemistry in general. And of course, this is just scratching the surface of the molecular orbital theory and its applicability towards organic chemistry. But until you learn a little bit more in your course, this is a good starting point for you to start identifying those orbitals and start seeing what type of molecular orbital interactions you have in your reactions based on the mechanisms that you are learning in your course. Later on, we're going to look more into the molecular orbitals and how exactly molecular orbitals help explain certain type of reactivities in organic chemistry, but that is the subject for a more advanced conversation. So I'll talk about that in a different video. And if you're still here, thank you for watching. If you learned something new today, you can tell me that by hitting the like button and leaving me a comment below. Your likes and comments really help in promoting my videos and help most students see those. Subscribe to the channel for more organic chemistry updates and tutorials. Watch this video next, and I will see you next time.